Okay, so in this problem, I'm going to be talking about circular motion as a general overview, and then I will go over a specific problem. Okay, so before all of our motion was linear, and which can be nice and very comfortable to use, but sometimes obviously things move in a circular path, which can be a little bit tricky and or not very intuitive. Compared to like a linear path. Okay, so what we have here is we have a circle like this, and I just want to in this first step I just want to like define a couple steps. So here's a circle, obviously. In the middle is the center point, and then from the middle, obviously, to the edge is the radius of the circle. Obviously, from one edge to the other edge is the diameter. Half of that, of course, is the radius. The radius is we're going to measure in meters, and then this angle here. Anytime you measure angles, you should use. Of course, you can use whatever you want, but you should use radians. Okay, you should use radians, but you can use degrees or whatever. But it's just easier just to use radians. All right. And I'll talk about that in just a minute. Okay, the other thing is, and then let's see here, what else? So when you're traveling around, let's say you want to go, you're here and you want to go all the way around the circle, right? That's called the circumference. And the circumference is this c, and it's defined as pi, which is roughly 3, times your diameter. So whatever your diameter is, just think of it as 3 diameters. Is the distance around the circle, okay? So 3 diameters. Remember, it's not really 3, it's 3.14. But just to give you an idea, it's like 3 diameters. But a diameter is just 2 radiuses, right? So you can say the circumference is equal to pi d, which are 3 diameters. You could also say it's 2 pi r, so those are the same things. So this is the circumference, and this is in meters. So if you want to know, like, if you're here and you want to go all the way around, like, how far is that in meters? This is how far it is. 2 pi r, of course, is your radius. Now, if you want to know, like, how fast you're going, obviously this is like a distance, right? The circumference is a distance. But in order to do velocity, you have to take your distance, which is your circumference, and divide it by time, okay? So it's 2 pi r, that's your distance, divided by time, and then that is your velocity, and that's in meters per second, okay? So meters per second, so velocity tells you how many meters you're traveling in 1 second. There's another concept you could use in circular motion, that's called the frequency. And the frequency versus where velocity is meters, the number of meters you're doing in a second, frequency is the number of revolutions you're doing in a second. So not meters per second, but revolutions per second. You want to do 3 revolutions in a second. You would start here and go 1, 2, 3. And so that would be 3 revolutions per second. Now there's the opposite of frequency, and that's time. Time is how many seconds in a revolution. So let's say you take one revolution, but it's really slow. And so let's say it takes you 5 seconds to do a revolution. So you go 1, 2, 3, 4, 5 seconds. 5 seconds in a revolution. Okay, so that's your time. So time is the inverse of frequency. Frequency is revolutions per second. Time is the number of seconds per revolution. Okay, and of course we have velocity, which is just meters per second. Now, if you want, so velocity is nice if you want to know, like I said, how many meters per second. But let's say you want to know how many angles you're moving per second, okay? And that's this omega. So omega, this is a Greek letter, looks like a W, right? But it's a Greek letter omega, and the lowercase one. And what it means is how many radians you're traveling per second, or like think of like degrees, right? If you're in that mode of thinking. So like number of degrees per second, but here we're going to use radians per second. So it's 2 pi, so 2 pi is how many radians you're going to do per second. So 2 pi is 2 times 3 roughly is 6. Okay, so it's roughly 6 radians per second, okay? And that's your angular velocity, okay? So the difference between angular velocity and just regular velocity is there's no r. See here, 2 pi, this is 2 pi r over t, this is just 2 pi over t. So it's missing an r, meaning I don't care how long its radius is, that doesn't matter. The number of angles you're going to traverse per second doesn't matter it doesn't matter how long your radius is, okay? It doesn't matter. So that's why when you do omega, which is just angular velocity, you pull out the radius because you don't care. You don't care about that. So once again, angular velocity, or omega, is just velocity just minus the radius because you don't care about it. Now, acceleration. Acceleration is very tricky. I mean, acceleration is very not super intuitive. Acceleration, really, there are two vectors in acceleration. There's what's called the tangential acceleration and the radial acceleration. So if this is our circle and someone's traveling around the circle, say like this, the velocity vector is tangential. So if the person's here or whatever it is and they're moving in a circle, the velocity is tangent to that circle. Okay, it's tangent to that circle. And the length of the vector is how fast they're going. So if they're going 3 meters per second, it's small. If it's 30, it's a lot bigger. So like the size of the vector is like how fast they're going, like their speed. But the velocity vector is always tangent to where they are. Okay. Now the acceleration has two components. It has a tangential component, which is obviously just like this. It's tangent to the circle. And it has a radial part, which is like this. Now, the radial part points towards the center, okay? Towards the center. Now, the radial part always points toward the center. The tangential part can be zero. There can be no tangential part of this if the velocity is constant. So meaning if the speed, like let's say you're going 3 meters per second, if you're constantly doing 3 meters per second, then the tangential acceleration is non-existent, and all you have is just radial. But once your velocity starts changing, like 3 meters per second, 4 meters per second, 5 meters per second, 6 meters per second, whatever, your velocity starts changing, then your tangential acceleration will also change too. And so instead of being zero, it'll start to grow like that. And then you'll have two vectors, right? Then you'll have this vector, your tangential acceleration vector, and you'll still have the radial vector. And so you'll have to add those two vectors together to find your overall acceleration vector. So if there is no tangential vector, right, and this is zero, then the only vector you have, the total, is just this. It's just this. But if you have this and this, then they add together, and it ends up looking like, maybe like this or like this, So yeah, so that's that. Now, so the formula for the radial acceleration is v squared, which is right here, which is 2 pi r over t. You just take that, you square it, over r, your radius, okay? And that will tell you how fast you're going in meters per second, okay? All right, so that's about it. That's just a general overview of circular motion. Now what I want to do is go into a specific problem, and then we'll solve it, and hopefully it'll make it, hope this makes a little bit more sense. Okay, we have a racetrack curve, and it has a radius of 90 meters, which is right here, and is banked at an angle. So there's a race car going around a racetrack, and the racetrack isn't flat; it has an angle to it, and the angle is 18 degrees. The coefficient of static friction between the tires and the roadway is 0.4. So there's a tire, obviously, and it's touching the road, and the friction between the tire and the road is 0.4. Now it says the race car has a mass of 1,200 kilograms, and it goes around the curve as fast as it can go without skidding. Okay. As the car rounds the corner, what's the normal force? What's the radial acceleration, which is this, and what's its speed? Okay, so this is sort of what it looks like. If you were looking down, imagine you're looking down from a bird's eye view. You can see the car going around in a circle, right? This is the radius. The velocity is going to be tangential to the circle, and then the radial acceleration is going to be pointed in towards the center. Now, this right over here, I've sort of drawn it in a different way, meaning I'm looking at the car. Imagine you're like standing in front of the car as it's approaching you. Okay, so the car is approaching you, and we can see this is like its headlights right here. This is its windshield, and it's coming towards you. Okay, so in this picture right here, the car is coming towards you. Now this thing is banked right here. It's banked at 18 degrees. You're like, why is it doing that? Because this car is going very fast, right? Maybe 100, 200 miles an hour in a circle. And so what would happen is if this wasn't banked, the car would fly off in that direction, right? It would fly off like this. And so the banking is keeping the car from flying off. So when we talk about the static coefficient of friction, you might be thinking, yeah, but the car's moving. That's not static, it's kinetic. Yeah, the car's moving this way, like it's moving towards you. But this way, back and forth like this, it's not moving, right? It's static. So yeah, so this way it is moving, that's correct. But this way it's not moving. And so when they talk about static, that's what they mean. So the car is here, and and so because the car is going, imagine the car is coming towards you, but it's going to go around like this in a circle. The center of the track is here, right? The center of the track is here, right? And then the angular, the radial acceleration should be pointing towards the center of the track. Great. So what I'm going to do is I'm going to take this car, which is right here, and he's right here. I'm going to make a free body diagram. So the weight, here's the car. The weight, of course, is going straight down, right? Straight down. So that's this. Here's the car. Weight's going straight down. Now the normal force. So this is the car is sitting on, or whatever, it's driving on this banked road, right? So the normal force is pushing this way, right? So weight's pulling straight down, but the normal force is pushing at this angle right here, which is 18 degrees, and I have that right here. Here's the normal, and it's pushed over because normal would have been here, right? It would have been up and down. But because this thing is banked 18 degrees, remember it was here, so it had to go, it had to move from here to here. And how far did it move from here to here? 18 degrees. 18 degrees. Now, there's also the force of static friction. Now you might be thinking, like, where's the friction at? Is the friction in this direction or is it in this direction? This is how I like to think about it. Imagine there's no friction on the car at all. There's no friction, and this car is going super fast. What's going to happen to the car if there's no friction? Well, it's going to fly off this way, so it's going to fly off in this direction. So if that's true, then friction needs to stop it. So friction has to go in this direction because the car wants to fly off that way. So we want the friction to go this way, and so that's what we have here. So the normal force is this. This is the normal force, and then the friction goes down like this, and that's what we have here. So we have the weight. We have the normal force, and we have the friction. And then, of course, what I did was I just took the normal, and I broke it up into its two components, into a vertical and a horizontal. And the friction the frictional force, I broke that up into a horizontal and vertical as well too. Okay, and so now what we can do is we can just use Newton's either first law, which says there's no acceleration, or a second law, which is there is. Basically, the first law is the forces are balanced. The second law is the forces are not balanced. Okay, so let's do y. So y means, let me just go back this way. So y means up and down, right? So is there acceleration in the up and down? So is the car moving up and down? No, it's not. So these forces are balanced up and down. So whatever this force is down here, this force is exactly the same. They're balanced. So there's no acceleration. So we can use Newton's first law for that. But if we're talking about in the x direction here, are we going to use Newton's first law? Is it balanced or is there acceleration? No, there is an acceleration. There's a radial acceleration towards the center of the circle. And because there is an acceleration, we have to use Newton's second law for this. So we use Newton's second law for the x direction, and we'll use his first law for the y direction. Okay, so let's do that. So I'm going to say, let me do it like this. I'm going to say the sum of the forces in y is equal to 0, right? And over here, we're going to say the sum of the forces in X is equal to mass times acceleration. Remember, because this is Newton's first law, and this is his second law. Okay? So in Y, let me just go here. We have this is going up, and these two are going down. So we have one going up, and these two are going down. So all we have to do is just write that in. So we have n cosine 18, n cosine 18, but that's the one on the top, minus the weight, that's the one on the bottom, and then minus fs sine 18. Sine 18 equals 0. Equals 0 because this is the first law. These all balance out. And so what you can do here is you can change W to mg. All right, this becomes mg right here. And then you can move mg over, and then this becomes n cosine 18 minus fs sine 18 equals mg. Like that. And then you could pull... Oh yeah, and then Fs right here. Fs can become the static coefficient of friction times the normal force, right? Then you can get rid of the F, and then you can pull out n. You can pull out the n and go n cosine 18 minus mu s sine 18 equals mg, right? And then of course you can just divide by cosine 18. Cosine 18 minus mu s sine 18, right? And then this goes away. And then you have n over, basically n equals mg over cosine 18 minus mu s sine 18. After you do that, the normal force is equal to 14,202 newtons, okay? So now we use Newton's first law because there is no acceleration up or down. Now that we have that, now we can do the second law, which is now for this one we're gonna do these. So this is pointing in this direction. The n sine 18 is pointing in this direction, and the fs cosine 18 is pointing in this direction. So both forces are pointing in this direction. That's because the radial acceleration is also pointing in that direction, right? So the forces are pointing in the same direction as the radial acceleration, which is correct. That's what you want, because that's how. Remember, in circular motion, these things are going to point. The radial acceleration is going to point towards the center of the circle, and this is the center of the circle. Great. So we have this plus this. Basically, this plus this equals the mass, which is like 1,200, I believe. Yeah, 1,200 kilograms, and then we just solve for acceleration. Okay, so all we have to do then is say n sine 18 plus fs. We'll change fs to mu s in cosine 18. Cosine 18 equals mass times acceleration. Right? And if you do this, you'll get, you can do all the math, and you'll end up with A. You can just solve for A. Basically, these are all numbers right here. Everything's numbers. It's simple algebra. And then you end up with acceleration equals 8.15. 8.15, of course, that's in meters per second squared. That's your acceleration. And remember, up here, acceleration is equal to v squared over r, right? So what I would want to do then is, if I want to find my velocity, which was part of the problem, I would say I would take A, which is 8.15, multiply it times r, which is 90, and then that equals v squared. That equals v squared. Of course, you gotta take the square root of both of those guys, and then you'll end up with the velocity is equal to 27 meters per second. Okay, and so yeah, so that's essentially it. Let me just highlight those. There's the normal force, there's the velocity, and there's the acceleration. Okay, so just in recap, what we did was is we looked at this car, and let me just make this right here. Yeah, we took this car and we put them on 18-degree embankment, and we figured out using basically the trick of the problem is do your free body diagram like this. Make sure the normal force is going this direction. Make sure the force of static friction is going in this direction. The weight's going in this direction. And then, of course, you need to understand that you have to use Newton's first law for the up and down or the vertical component, and you have to use Newton's second law for the horizontal component. And that's it. And then you solve for the normal force first, and then you can solve for acceleration next. And then once you have acceleration, you can get velocity. And then that's it.